I'm going to present you Guy Somberg, who has been programming audio engine for his entire career, from low-level audio mixers in slot machines to a contribution in very big games like BioShock 2 or The Sims 4, and is going to talk today for us about game audio programming.
All right. Thank you. So thank you all for coming to Game Audio Programming. A little bit more about me. I've been in games since 2002, and I've owned the audio engine at every company I've ever worked at, either for the entire company or just for the individual game I was working on. And in that time, I've shipped lots and lots of games, everything from, as you said, slot machines up through AAA titles and indie titles and everything in between. I am also the editor and author of several chapters in a couple of books on game audio programming titled Game Audio Programming, Principles and Practices. So if you want to learn more about it, those are great resources. And so today, I want to give you, I don't have enough time to go into too much detail about it because there's so much about game audio programming. So it's basically an overview of the kinds of problems that we solve as game audio programmers. And so the first thing I want to discuss is kind of how I think about game audio programming. What is game audio programming? I have this definition. It's working with sound designers to create awesome aural experiences. But it sounds like a very generic, like not really much of a definition because it can apply to just about anything. But there's a couple of key phrases in here, and that is working with sound designers. The sound designers really are the customers of all of the tech that I write because they're the ones who are making awesome sounds. And it's not about realism, it's not about performance or low latency. So some of those things are part of it, but it's about making the game sounds awesome. And so that is the really, ultimately, that's what we care about, that the game sounds awesome. That doesn't really help to answer the question of what do game audio programmers do all day? And the answer to that question really depends on what kind of game audio programmer you are. In the last few years, the field has kind of expanded quite a bit. There's technical sound designers who are actually sound designers who have some ability to program and are able to go into the code, add hooks, maybe prototype some new features that the sound designer, that maybe another game audio programmer can take and expand upon, or that a non-audio programmer can take and kind of formalize. There's an audio engine programmer who kind of lives in that space between the game engine and the whatever kind of audio middleware you're using, whether it's built in-house or a third-party library. DSP programmers will live at the low level and work with mixers and make their own custom effects. And there's other kinds of people who work in all these spaces in games. So the answer to that question is colored by what kind of game audio programmer you are. I'm an audio engine programmer. I live in the middle space where I make tools. I author all the engine that connects the audio to the game. So here's the kind of things I do. I'll set up game hooks. The #1 bug in every single game ever for audio is, why is my sound not playing? This is just throughout history. So we also have to understand the tools that we're using at a very deep level. Because we have to help our sound designers design very complex events that they may not have the intuition to create, but that are just the functionality that's available right there. We do all kinds of real-time things, a lot of tools, a lot of game features, and I'll go into what those things look like throughout this talk. But one thing that people at the game audio engine programmers like me don't do is we don't write bytes to audio buffers. That, from my perspective, it's a solved problem. I'm not dealing with anything like that because middleware is king in game engines. If you're in Europe or the Americas, you're probably using either Fmod Studio or Audio Kinetic Wise. If you're in Asia, Japan, China, Korea, you're probably using Cry-ADX2. Or if you're using Unreal Engine or Unity, they will have their own middleware that is becoming more and more capable. So what do these tools look like? This one is FMod Studio. And what we're looking at here is a music event that has low, medium, and high intensities with an automatic transitions across intensities as you change that parameter on the beat with a stinger to hide transition artifacts. And all of this is exposed from the programming side through a single play event call and an exposed parameter that is for the music intensity. This is audiokinetic-wise, and what we're looking at here is a glass bottle impacting a surface. And there are parameters that switches which sound it's playing based on the hardness of the target surface, and then it applies a low-pass filter, pitch adjustment, and volume adjustment based on the force of the impact. And again, all of this is exposed with a single play event call and a suite of exposed parameters. This is Cry-ADX2. I'm less familiar with this tool. I'm pretty sure what we're looking at here is a music track with parameters adjusting various controls. So this is our starting point. This is what we have to begin with. And so the question is, where do we go from here? What do we start with? And so I want to actually take you through my bootstrapping process. When I'm working on a new engine, I get this tool, and then what? Build a state machine. But I want to show you, before I even go there, I want to show you the code, the entire source code for an audio engine using the FMod Studio low-level engine. And I'm going to go about 99% light speed through this because it's not about showing you the individual lines of code. It's about the shape of what this thing looks like. So here we go, very quickly. Here's our audio engine. It is a singleton because we only have one audio engine in games. So we have our static init, update, and shutdown functions, and a bunch of functions to load and unload sounds, set 3D listener position because 3D panning is a given. Very often it's vector-based amplitude panning style, but object-based panners for VR and AR are becoming far more common and prevalent. And then a bunch of jukebox functions, play, stop, pause, and then functions to set parameters on the individual playing channels, 3D position, volume, etc. We're going to use the Pimple idiom. Here's our implementation. And then our data is a map of the loaded sounds and the playing channels on those sounds. Our update function just checks the current playing sounds to see if any sounds are stopped, erases those sounds from our tracking, and updates the system object. Load and unload sounds are matched pairs, so we first check to see if the sound is loaded. Then we either load or unload the sound, and then we add or remove it from our map. Play sound is a little bit more complex. First, we check to see if the sound is loaded. If it's not loaded, we load the sound. And then if that sound failed to load because the file is missing or it's corrupted for whatever reason, we can exit early. And then we play the sound and set all of its parameters, 3D volume, or 3D position, volume, panning, pitch, whatever else we need to. The rest of the functions all follow this pattern. It's set, channel, whatever. We look it up, and then we set its parameter. And they're all boring, so I'm not going to go into all the details of all of them because they all follow this pattern. All in all, it's about 250 lines of code to bootstrap this code. To bootstrap this, took me about an hour and a half, but I knew what it was supposed to look like in the end, so it might take someone else a little bit longer. But I want to take this as our starting point, and I want to add some features to it. I want to add fade outs, async loading, and virtual sounds to this engine. Now it's tempting to just jump right in and implement these features, but first I want to give a word of caution about what I call heuristically grown update loops. And this is where you have a system like this, and you need a feature. So it's like, I'll put it there, because it makes sense to put it there. And then you add another one, and another one, and another one, and another one. And by the end, you end up having to have these horrible heuristics to guess what state you're actually in. And this is why you end up with this horribly tangled mess, and why nobody wants to go in and maintain that horrible audio engine code. And I have seen this happen a lot of times. And down this road lies madness. Do not do this. Instead, take a step back and note that each playing channel has a life cycle. And because of that, we can represent this life cycle with a state machine. And once we have these states, then there are great hooks, places to add new features. And the reason that these heuristically grown update loops appear, especially in audio code, is because this is what our state machine looks like right now. This is it. This is the entire state machine. So let's start with this state machine and build the three features I mentioned before. First feature is fade outs, where we're just going to say Optionally, when you say, I'm done with the sound, stop it, there's an optional fade out. Interface will look like this. Our stop channel was already there. We just added the fade time seconds to that. So we'll go to our state machine. When you request a stop, we'll put it into a stopping state. We'll wait for that fade to complete, and when the fade completes, we're in a stopped state. And that's it, but we've added states to our state machine, and now we've implemented that feature by adding these states. Let's do another one, async loads. So all of the code that I showed you was actually loading files synchronously. It would actually block waiting for the sound to come off the disk or the network or wherever. So instead, we're going to load these things asynchronously. Here's what the interface might look like. You register your sounds up front and then load them kind of by their ID containing all the properties of that sound. Again, we'll start with our state machine. Now here, instead of creating a sound from the ether and playing it immediately, we will create a sound from the ether and put it into a one-time initialization state. And I'll go into more what we do in that initialization state later. Once we've initialized it, we'll put it into a two-play state, which is a state of sounds that are ready to play. And notice that that box is bigger. We'll come back to why that's bigger in a little bit. But, and then once we've played the sound, then we can go into the playing state, and the state machine takes care of the rest. But all that is only if the sound is already loaded. If the sound isn't loaded in the two-play state, we can queue it for load, go into a waiting for load state, and once it's loaded, come back to two-play, and then send it through the state machine. Now there's one last arrow we need to do to add to make this complete, and that is now we've added some non-zero length of time between when you've requested that the sound is played and when the sound actually gets played. And in fact, it can even happen in the same frame, play sound, stop sound immediately. And so we need to add one last arrow from to play straight to stopping if the sound was stopped before it ever had a chance to start, either while it was loaded or while it was still being queued for load. And that's it. We've now implemented async loads to our sound engine by adding these states. Last feature I want to add is virtual sounds. Now this is a little bit more complex because virtual sounds are sounds that are important enough to track, but they're not important enough to hear. So a great example would be like a campfire, because you want that campfire is going to have some sounds of like popping and crackling and the flames. But if that campfire is 100 meters away, I'm not going to hear that. It's not going to be a meaningful part of my mix. So we can just cut it out entirely. But I still need to know, because then if I approach the campfire, I need to start the sound back up. So here we'll have the interface for this will be some private function called shouldBeVirtual. This isn't something that's exposed. It's an internal function that'll use some heuristics to decide whether or not this sound should be virtual right now. I already used the example of kind of if it's outside the max distance of the playback. We also have some very complex rules where we have an implementation of Walter Murch's rule of 2.5 for max within radius to kind of keep the mix in check. So let's go ahead and implement this feature. The one thing that we do with the sounds, when a sound is playing and we decide that it should now be virtual, we don't want to cut it off immediately. We want to give it a quick fade out, quarter to a half a second, somewhere in that range. So we'll add a virtualizing state to track that. So when we decide we should be virtual, we move to virtualizing. But then if during that quarter to half a second we change our mind, because maybe I was outside the range and then I went right back into the range, we can fade right back up to full volume and go back to playing state. But if we don't do that, if we continue to virtualize, once that fade is done, we can stop the sound, release its resources, and go into a virtual state, where now the sound is much cheaper. And then in the virtual state, all we have to do is check to see if the sound should still be virtual. If it shouldn't be virtual anymore, we jump up to the two-play state. But this is a little bit tricky because we want to do a couple of things differently when we are de-virtualizing a sound. We want to fade it up, give it a quick fade up, and we might want, if this sound has kind of an intro section, we might want to skip the intro section so that it doesn't sound like it's starting from scratch. So in that case, what we add is a new de-virtualized state. Now it's tempting to implement this as like a bit field or a flag, but it's such a transient state. It's going to exist for basically one frame ever. It's wasteful to store a thing that will just not exist for more than a moment, and just having a new state that we can just switch on in our state machine logic is much more efficient. So the arrow actually goes both ways. If we're in the two-player devirtualized state and we change our mind, we say, you know what, this sound should be virtual after all, we can jump straight to the virtual state. And the last arrow we need to draw here is that virtual sounds can still be stopped, so we could go straight to the stopping state. Now you notice there's a lot of arrows coming into the stopping state that could go straight to stopped. You can do that if you want. I like the cleanliness of everything going through stopping into stopped, but some of those arrows, like from virtual or two-played, it could go straight to stopped instead of stopping. And I want to finish the state machine right here, because this state machine is all you need to ship any kind of game. I have shipped lots of games with this state machine. I've shipped Hellgate London, Mythos, BioShock, The Sims, a lot of Telltale Adventures, which actually didn't need any of the virtualization text. We just sliced that off. And I've been developing the precise nature of the state machine over time, so it's had some variations. But this state machine right here is extremely effective and is basically all you need to manage the state of a playing sound. So let's see the code. I'm going to go even faster this time, 99.9% light speed. You can't actually reach light speed, of course. And I'm going to skip a bunch of boring parts, because otherwise we won't have time for anything else in this talk. So here we go. Here's our audio engine. It's a little bit bigger, but here's the new section. We have our definition of a sound and functions to register and unregister these sound definitions. The thing about this little block of code is that it's fake. You wouldn't actually do this precisely in a real audio engine, because you would have a spreadsheet or a database file on disk or somewhere that would tell you, here are all of your sounds and here are their properties. So it wouldn't look exactly like this. But the thing is, if you wanted to do this, what I have here is shippable. You could actually do this. It's also boring, so I'm not going to talk about the details of sound loading beyond that. The rest of it is all the same, except that we've added this fade out time to the stop request and a delta time to the update function. Okay, I lied about not showing any boring bits. This is the function to load a sound, and the reason I'm showing it is because here's the magic. When you're using the fmod API, that is the magic that you need to effect the async loads, to actually tell fmod, load these sounds asynchronously. Here's our channel object, which is more complex by virtue of the fact that it exists in the first place. Notice here's our state machine, all the states for our state machine. And the underlying implementation, we have a reference to the pimple. We have our channel objects, the fmod channel pointer, which is what we had before, all we were storing before, and a bunch of data for managing how we play that back, and some functions to help with all that as well. And we'll take a look at some of that in a little bit. The play sound is now much simpler. We don't actually have to play the sound, check for load, all that other stuff. We just allocate memory, and the state machine takes care of the rest. Same thing for stop channel. If there's no fade, we can stop the channel immediately. But if there is a fade, we just set a flag saying, hey, stop request, start the fade, and the state machine takes care of the rest. So all this code actually becomes more efficient in the main thread, because you're in your game's loop, because you're no longer actually calling into your audio middleware from anywhere other than your audio update function. The rest, we have all these same boring functions. They're still boring, but they're boring in new and exciting ways, because now instead of calling set volume, we're just storing the volume, and the state machine takes care of the rest. The update function is very similar. Here's the new bit. Instead of checking to see if the sound is finished, we update our state machine and check to see if the sound is stopped. Let's go and introspect that update function now, which will take the form of a giant switch statement in which a miracle occurs. That miracle, of course, is a wall of code, for which I'm sorry, but we're going to do this step by step. First, initialize state. Notice it's empty with a fall through. And the point of this is not that it's doing anything right now in the code that I'm showing, but that it's a hook for you to add new features. And we'll come back to some of the stuff you might want to put there later. Here's our devirtualize and two-play state. First, we check to see if the sound is stopped and put it in the stopping state. We check to see if the sound should be virtual. And if it's a looping sound, we put it into the virtual state. If it's a one-shot sound, we just drop it on the floor. Don't even bother playing it at all. And the reason for that is that most one-shot sounds are They're quick impacts. They're things like footsteps or gunshots or barks or things like that where it doesn't, if they're not important enough to hear when it first starts playing, they're not important enough to hear at all. So then we check to see if the sound is loaded. If not, we queue it for load, put it in the loading state. And then we call the play sound and set parameter calls. And note, this is exactly the same code as the other audio engine I showed. It just has all the state machine stuff around it. Here's our virtualized fade in for our channel, for the virtualized, or the devirtualized state. And then we move on to the playing state. The loading state, we just check to see if the sound is loaded and go back to the to-play state. For playing, we update our channel parameters. And this is a function that is going to collect all of the information that you need to adjust the channel's parameters as it's going. Its volume, its pitch, any event parameters, anything else that's kind of that you need to collect to change how the sound plays at runtime and apply it in that one function. We check to see if the sound is stopping, move to the stopping state, see if it should be virtual, start the fade, and move to the virtualizing state. And this is our fade up for if we switched from virtualizing out back to virtualizing in. When you're stopping, we update our stop fader. We still update our channel parameters because the sound can still be moving around in 3D space while it is being stopped, while the fade out is happening. We check to see if the sound is stopped and move to the stopped state, which is the world's most boring state. Virtualizing, we update our fader and the channel parameters, which could inform the question of whether or not we should be virtual. We check to see if we should not be virtual anymore, move back to the playing state and do the fade in. Otherwise, we check to see if the fade is complete, release our resources, and move to the virtual state, where we check to see if the sound is stopped and check to see if the sound should not be virtual anymore. And that's it. So this is, all in all, about 600 lines of code. And it's almost all state machine code. Like all the audio functions that we had from before, they're still there. They're still in the same order. They just have all the state machinery around it. This took me about 3.5 hours to go from one to the other. And so the question is, so what? Like we did this, but what did we get from it? Well, now that we have the state machine, we can add new features easily and cleanly. I'm going to show some examples of the kinds of features you can build and where they would go. Let's randomize the volume and pitch of playing sounds as they're played. Technologically, it's trivial. We can just pass that information to our middleware. But we need to pick which volume and pitch we're going to use. And you do that in the initialize state. And the reason you do that in initialize instead of to-play is that if the sound gets virtualized and then devirtualized, you want to make sure that it plays back at the same volume and pitch as it was before it got devirtualized. And then you include that random volume and pitch in the update channel parameters, which is called already in a number of states. And that's it, we're done. We've implemented this new feature by applying it to the appropriate states. Let's reduce the CPU usage for virtual sounds. There's lots of ways to do this, but the simplest one is just to update them less often. So in your update loop, you only update the virtual sounds every n frames or seconds, however often. But you have to be careful with this because you don't want every 10th frame to be the frame that is slow because that is the frame that you update all your virtual sounds. So you want to make sure you stagger your updates for update times for all of your virtual sounds. And that's it. We've now made virtual sounds cheaper by hooking the one state that we're interested in. The last example I'm going to give is playing groups of sounds together. We had this feature in Hellgate London where sound designers could say, I want this one sound to play these 4 other sounds together and manage them as one unit and control their volume kind of as a group. So to implement this, we store a channel group and a vector of subsounds in our channel object. We make sure that we load all the subsounds in the loading state and play all the sounds together in the to-play state and assign them up to the channel group during that state. And then we update channel parameters to be aware of this new channel group hierarchy. And that's it. We've implemented this feature. And we've had, the point of all these things is we've had hooks, we've had places to add and apply all of these features throughout the lifetime of a playing channel. And so this is how we bootstrap. This is the very beginning. This is the first thing I do when I'm starting a new game and I'm either deleting the horrible old audio engine, or there is no audio engine, and I'm just coming in and starting from scratch. But then, once I've done this is, I'm practiced at this, I can do this very quickly. What next? What other things do we do? Now here, I'm gonna show less code and more kind of overview of the kinds of features that we're gonna build. I wanna talk about two specific features, ambience and real-time mixing. But first, a little bit about low-level versus Studio API. So fmod has a low-level API that I was using in all the source code examples that I was showing, where you have fmod sound, fmod channel, and those are applying to single wave files, like wave or MP3 or OGG or whatever compressed file, single files. So you're playing a single file back. And the thing is, what about that fancy tool that I showed with like the music event with all the timing and everything? Well, here is the kind of code you write for low-level API. You have your system objects, and you call create sound and play sound. Here's a Studio API. It has more or less the same shape. You're just using different functions. So instead of calling create sound, you call get event and create instance. Instead of system play sound, you call event instance start. So it's very much a find and replace operation. You find things in the left-hand column, replace them with the right-hand column. There's a little bit more fix-up you have to do. It's not quite as trivial as find and replace, but it's not a complex operation. And all the state machine machinery does not change when you do all this stuff. So 20 minutes later, you've done all that. Now what? Well, off the top of my head, here's a short list of some of the things that you might want to do. Now, not every game will need all of these things, but every game will need at least some of these things. And some of them are easy, some of them are built in, but you still have to think about them and be aware of how they interact with your game or with the way that the sound designers are going to be using them. Now, I want to talk about two specific features, ambience and real-time mixing. So for ambiences, they're the background sounds of your game. We're talking things like the room tone, wind, birds cawing in the distance, stuff like that. It's tempting. As a result, because it's the background, it's the ambience, it's not the most important thing in the game, but it's important that it's there, but it's not the most important thing that you're hearing in general. So you want to reduce the amount of space it occupies for both memory and disk, and you want to reduce the amount of repetition, because your players will notice when things repeat. Now, it's tempting to create a long loop, but that fails on both space, because it's going to be a large file, and repetition, because your players will notice, well, there's that gust of wind followed by the taxi honk and the pigeon coo, because it's baked into your long file. So the question is, from shorter pieces, I have no long loops. From shorter pieces, how do we construct a better, more organic, dynamic ambience? There's ultimately two components to a good ambience. There's loops, things like room tone, wind, and the walla of people talking in a room. And there's one-shots, things like bird calls, car honks, and I kid you not, babies crying in the distance, which was one of the creepiest things in Hellgate London that our sound designer, that was the first thing that came to his mind. Like, I'm gonna have babies crying, it's gonna be awesome. So today, unfortunately, I only have time to talk about the loops. I'll touch on the one-shots a little bit, but we'll go into detail about how to implement loops. So ambience loops are this complex construct comprised of all these parameters. But really, it's all about rolling dice. And the best way to describe this is with an example. And so let's assign values to all these parameters: play chance, play time, silent time, fade time, and volume. And we'll put them up here at the top, along with the timeline. And I'll describe kind of how the algorithm works with all the dice rolling. So the first thing we do is we roll for play chance. Roll the dice. We rolled a 15. Well, 15 is less than 85, so this time we're gonna play. So now we roll again. We roll for play time, which is between 15 and 30 seconds. We rolled 23.6 seconds. We roll for the fade time, which is between 2 and 3 seconds. We pick 2.2. Roll for volume, between minus 12 and minus 9 dB. We pick minus 10.1 dB. So what do is we play for 23.6 seconds. We fade from our current volume, which is silence, up to minus 10.1 dB over 2.2 seconds. And then we wait for the end of that 23.6 seconds. End of 23.6 seconds, we roll the dice again. Roll for play chance. This time we roll a 72. Roll for the other parameters: play time, fade time, and volume. We pick 18.2, 2, and minus 9.2. And so what do we do now? We play for 18.2 seconds. We fade from our current volume of minus 10.1 dB up to minus 9.2 dB over 2 seconds, and wait for 18.2 seconds to pass. Roll the dice again after 18.2 seconds. This time, we rolled a 92 for play chance, which is greater than 85, so this time we go silent. This time, instead of rolling for playtime, we pick from the silent time, which is 10 to 20 seconds instead of 15 to 30 seconds. So we pick 12.5 seconds, a 2.8 second fade time, and so now we fade from our current volume of minus 9.2 dB down to silence over 2.8 seconds and remain silent for the next 12.5 seconds, at which point we roll the dice again. So this creates, you can have a relatively short loop and it can fade in and out and becomes this very organic, dynamic piece where instead of just having this loop, you have, that has all these fixed components, you can layer multiples of these things together. And you can have your kind of room tone, your basic room tone your basic room tone or whatever, your base layer that's always playing but kind of fading up and down, and combine it with these layers that will come in, they'll come out, they'll start, they'll stop, because you've adjusted their play chance so that they're not always there and their volume is appropriately mixed for everything else. So all this is just for loops. You want to complement this with some randomly triggered one-shot sounds, like those babies crying that I mentioned. So with the design tools like Fmod Studio and Audiokinetic Wise, you can actually encode these as effectively looped sounds. If you're using Fmod Studio, there's actually it's called a sound scatterer module or instrument. And that has all these timings built in. It's gonna pick a random 3D panning, it's gonna pick a random volume and a random pitch variation, and it's gonna play it on some timer. And you can, that's one thing, and you can put a loop region around that and play it. And now it becomes just exactly one of these loop regions that you had before. You can also do it by hand, if you want a little bit more control and flexibility, using a dice rolling algorithm similar to what I just showed with these ambience loops. Unfortunately, I don't have time to go into the details of that today. There are some subtleties around positioning and panning and stuff. That's ambiences. This is the kind of system that is, it's very important to build, but it's not obvious that you have to build it from the outside. But it makes for a very effective a very effective and awesome aural experience. So the next feature I want to talk about is real-time mixing. The thing about game mixing is it's very complex. We have all the same challenges as offline mixing, just hundreds or maybe even thousands of sounds being thrown at you at the same time. And how do you control that? We have many of the same tools as offline mixing. We have VCAs, we have buses, we have a lot of DSPs at our disposal. But we have to make all the decisions about what to do in real time. There's no, trying a thing and seeing if it works. You have to make the decision, make the call. So we have a lot of tools at our disposal to do this in real time. The simplest one is just culling. Don't play a sound. I already talked about the virtualizing sounds that are not contributing to the mix or should not contribute to the mix. And we'll have rules based on, for example, Walter Murch's rule of 2.5 for either content replacement or other kinds of things to kind of control that mix. We have mixer snapshots where we have a bus hierarchy and we can say, while you're on fire, adjust the volume and the DSP effects in your bus hierarchy in this manner. And that we can layer multiple snapshots together. So if you're on fire and poisoned, then we can do the things for on fire and poisoned together. And they can override each other and all these other things. These are all built in or things you can implement without too much trouble. We also have a large suite of DSP effects, usually baked into the middleware and with hooks to implement your own. Another feature is called HDR audio. And this one is interesting. What you do is define for your game a dynamic range, a desired dynamic range. In this example, we've picked 100 decibels. And then on top of that, you assign each sound or event in your game a dB value. So here in this example, the bee has a dB value of 20, and the gunshot has a dB value of 130, which is, note, above the dB range for our game. So as the bee comes in, there's nothing else going on. Our dB range is plus 100. And so the bee just plays. But now the gunshot plays, and it kicks up the dynamic range of the game up to 130, because that's where it is. But the total dynamic range of the game is just 100 dB, so the lower bound on our dynamic range is 30 dB, which is above the value for the B, so the B gets cut off at that point. Once the gunshot is finished, then our the upper range, our dB range decays down to its regular value. And once it reaches that 20 dB value, then the B can fade back in and continue playing. This kind of tech you can build yourself. It's built into Audiokinetic Wise. The challenge is here that you have to assign each sound this dB value. And that implies an importance to that sound. There's an implication that louder sounds are more important. And so there's this fundamental problem, is that the game's mix is just messy, and it's contextual. You can have dozens or hundreds or thousands of events playing all at once. And these traditional mixing techniques, like snapshots or prioritization or HDR, they're useful. We don't want to throw them out, but they're insufficient when faced with just the magnitude of communicating to the player what is important right now. So in my current game, Torchlight Frontiers, we had some early attempts to solve this kind of problem. We had this feature request, which I never actually implemented, thank goodness, nearby monster count. And we tried to categorize sounds, like the goblin brutes were more important than the goblin warriors, and it just didn't work. None of those things really solved the problem. Here's a screenshot from Torchlight Frontiers. Right now, you're playing the robot character, the Forged, in the middle, and there's, what, like 1, 2, 3, 4, 5, 6, 7, 8 goblins on the pier in front of you, and notice in the bottom left, there is another goblin below, underneath the logo. There's another player, a Dusk Mage, on the pier heading in your direction, and then there's all the water sounds, there's all of the creaks and the sounds from the ropes and all the fishing equipment that's there. And all these goblins, some of them are looking at you, some of them are attacking you, some of them are interested in the other player. Some of them haven't noticed you yet, some of them are yelling. There's just a lot of stuff going on. How do you know what's important and what you should be paying attention to in this situation? The solution we came up with was a system called Importance, which is actually one of the most important mixing techniques in our game. I want to give a big shout out to Tomas and Paul from the Overwatch team at Blizzard, who implemented the same feature in their game and sat down with us and kind of described how their implementation of it worked. And we implemented our own kind of clean room implementation of this. So this is heavily inspired by Overwatch's implementation. The algorithm is actually very simple. We assign each object that is or can play sounds an importance score. We sort all the objects by their score, place them into buckets of importance, and apply an effect to all the sounds in the bucket. And there's some subtleties, like you have to make sure that you can crossfade, so as the sound moves from bucket to bucket, you need to be able to change the parameters of the importance effects. But it's ultimately a relatively simple algorithm. So let's dive into the details of this. The importance scores are going to be extremely game specific. No two games will have the same meaning for what is important. Whether it's a multiplayer game, a single player game, an action RPG, a real-time strategy game, the importance of a thing will vary. In Torchlight Frontiers, we gave them 4 categories of scores. The identity of what this thing is, how far away from the player it is, how kind of big or dramatic this thing is relative to the other things on the screen, and what is it doing? What is this creature or this thing that is playing sounds? What is it doing, and is that important to you, to me, the player? We assign each of these categories a weight, and the total importance score is just the weighted sum of these individual components. So I went and took the screenshot and applied these scores to these. It's kind of arbitrary, but it's close to what the actual scores would be in this situation. And so now we have an idea of what's important. So, and we have actual scores for everything on the screen. So we take them, we sort all the scores numerically, highest to lowest, and we assign them into buckets. So let's say our highest priority bucket has 2 sounds, next priority has 4 sounds, the next one after that has 5 sounds, and everything else is just in the lowest priority bucket in this example. Now we can look at it with colors. And we can see here, now all of a sudden, I'm the most important thing. That goblin in front of me is also the most important thing. And we can see how the importance of the things that are around me varies. And you can see actually on the far right, that goblin over there is more important than some of the other goblins who are closer to me. So I will hear his sounds better than some of the ones who are closer to me but haven't noticed me or are attacking another player, or for whatever reason they have these lower scores. So now that we have these buckets, we need to apply an effect. In Torchlight Frontiers, again, we apply a volume, a peaking filter, and a high shelf filter. Implementation detail in Fmod Studio, which is our audio middleware. There you have a multiband EQ, which allowed us to implement the peaking and high shelf filters together. But here's what we did. We have 5 priorities. At the highest priority, we apply a peaking filter to the high end, so it sounds more prevalent. Second priority, there's no change. Third priority, we just reduce the volume a bit, and at the lower priorities, we apply varying levels of volume reduction and high shelf. And as soon as we turned this on, it lit up this feature. The game just cleaned itself up. All of a sudden, you knew what was important. You could hear the things that were important and relevant to you right now. It was like magic. It was beautiful. So that, I hope, gives you a flavor and for the kinds of problems and the kinds of shape of what audio code looks like. It really is just scratching the surface. I wish I had a whole conference that I could just stand here in front of you and talk about all the cool stuff that we do. If you want to learn more about game audio programming, I highly encourage you to get these books. There are articles. These are articles from many of the game audio programmers in the industry who are very awesome. I learned a lot by editing these books, and I have several chapters in each one, and so there's great content in all these books. At this point, I have about 7.5 minutes for any questions. So,
thank you very much. Any question here? Okay, first.
Have you tried using more dynamic software like Alias or something to in-game creation? To sort of have in-game triggers for dynamic effects and stuff like that?
So I didn't catch the name of the software you were mentioning.
Alias, but it was just an example. There's several.
So there is some interest in that kind of thing, but the challenge is that the sound designers want a lot of control, and there's so much content to create that adding these tools usually goes into kind of the sound designer's offline tool suite. So if they want to author a thing, they'll grab a new tool and then they'll go crazy with, in their Pro Tools sessions and make the stuff and then plug it in. So there is some interest in kind of more runtime authoring of sounds, but there's not a lot of software that integrates cleanly with the game engines that people use. There some exists, but it's just not a thing that that I've had much experience with, and that my sound designers have really asked for in the games I've worked on. But there's a lot of games out there. So.
No questions?
In your mixing scenario, it sounds like it's very particular to what you are doing. Mm-hmm. It's the dynamic mixing that you've described. It works probably very well for that. Do you think that it would work like the same in other games like open world?
Oh, absolutely. Yeah. this idea of importance, first of all, we were inspired, the implementation we have is heavily inspired by Overwatch, which is a drastically different game. It's a first-person shooter, with a team-based first-person shooter with very, very different rule sets. And so I think that this kind of importance system would work, like, it would be the first thing I would build. If I were starting any new game from scratch, I would build that state machine, and then I would build that an importance system. Like, it would be among the first things I build, because it makes the mix, it just cleans the mix up so effectively, because it doesn't encode at authoring time, it encodes at runtime how important a thing is. Because how important a thing is changes. The example, I showed a bunch of examples from my game. Example from Overwatch is that if you have footsteps, are footsteps important? Well, no, but what if you're a sniper and you're looking in your scope? Are footsteps important? They're more important. What if they're my teammates' footsteps? That's not so important, but if they're an enemy footstep, well, that's really important. So all of a sudden, you scope in, and the mix changes. Those footsteps, your enemy footsteps will become louder. Your friendly footsteps will become quieter. So this is, every game is going to have its own categories of rules for what makes it important, what counts as important. But the principle of like having, of describing at runtime what is important and having that be an effect on the sounds is, I think that is kind of universal.
So you mentioned the state machine as one of the first things you would do. I suppose this was an implementation like in a 3-hour span, as you said. Mm-hmm. I suppose also it's one of the main things that affects performance. So you have any other best practices to implement this, like using state pattern or something like that to make it more efficient, or would this be like good enough?
A good question. For most games, what I showed, or some variation of something like that, is good enough. Kind of the next step that I do if I have a game that is more performance sensitive is I'll actually move a big chunk of that processing onto another thread. I have a pattern. I gave a talk at GDC a few years ago where I kind of talk about the mechanics of doing that. But it's basically avoiding spending time in audio processing. Can't talk. Avoiding the audio processing time in the game logic will improve your frame rate, because you might have a whole bunch of sounds, but you don't need to, the game simulation is not interested in that. So that's why moving it onto another thread allows you to control, like, well, the sounds that are playing are just kind of updated every tick. It allows you to have a very fast tick rate on sounds if you need that, if you care about it, because you maybe need a very fine-grained parameterization of the fade times or whatever. So it allows you to do that kind of control. I have actually never had my audio logic show up meaningfully on a profile in any game I've worked on. I know that there are some games that are more performance sensitive where that has happened, but those people can talk about what they've done in that context.
Thank you very much.
Oh, are we out of time?
Yeah.
No, okay. If we're out of time, we're out of time. I'm going to be around. I'll come outside, so come talk to me if you have more questions.